Bismillahirrahmanirrahim. In this video we will discuss the implementation of multiplexer using the different ways. We discuss the 4 to 1 multiplexer. Here is a logic diagram of the 4 to 1 multiplexer. It consists of 4 inputs, 1 output and 2 control knobs. The control knobs have the situations 0, 0, 0, 1, 1, 0 and 1, 1. At one time only one input is implemented on the output depending on the condition of the control switches. When at control 1 is 0 and control 2 is 0, also 0, it passes through the not control 1 and not control 2, and here it goes through this input 1 AND gate, and similarly it also goes to the input 1 and input 1 is implemented on the output. When at the control 1 is 0 and control 2 is 1, when this is 0 it goes to the here X, and when it is 0 it is 1, it can't pass through the not control 2 because it becomes 0 after passing through the NOT gate, so it passes through this wire and go to the here, so input 2 is implemented on the output. Similarly, when the control 1 is equal to 1, it can't pass through the NOT gate, so it will pass through the here and go to the input 3 AND gate, and when the control 2 is 0, it passes through the NOT gate and become 1 and goes to the here, and here the input become 1 1. We take the input 1 1 because when 0 multiplied by 1 we use the AND gate here. When 0 multiplied by 1 it becomes 0, so the output becomes 0. We have to attain the output, so we take the input here 1 1. It's compulsory. So at the fourth condition, when the control 1 and control 2 both are 1 1, it passes through the simple wire, and input 4 is implemented on the output. Now we discuss the methods of implementation of the given multiplexer in the Verilog HDL code. Here is the first method of gate level implementation. He simply module the file name and output input variables. Here it declare the output and input, and in wire and declare the wires. Here in the NOT gate he declare the control 1 2 and not control 1 2, which is here control 1 2 and not control 1 and not control 1 2. And after this he declared the AND gates here, which are W X Y Z, 1 inputs. These are the AND gates W X Y Z, from which the input 1 2 3 4 are passes. These are 1 inputs and control. After this he declared the not controls and control situations, because it denotes to not control denotes to 0 0, and not control control 1 denoted to 0 1, it denotes to 1 0, and control denoted to 1 1. It has the 4 cases. So we implement it to the Proteus. Simply we copy this and go to the Verilog HDL file here, and paste it here. Now we run this. Here it shows some error. We have to change the file name here. File name is lab6. Now we again run this. This time it's running. We can see that the analysis and synthesis and analysis and elaboration runs successfully. It takes some time. Here the full compilation was successful. Now we can see the RTL view from here. And here is the RTL view of this. Here is the control 1 and control 2 knobs and input 1, 2, 3 and 4. Here is a single output. Here X, Y, Z are the W, X, Y, Z are the 4 gates, and here is a wide OR gate. Here is the situation of 1 1, and here is 0 1, here is 0 0, and here is 1 0. Now we go to the university program VWF. Here we insert the node here, node finder, and list it here, paste it and click on OK and OK again. Here is we can see that control 1, control 2, we set the control 1 and control 2. When the control 1 and control 2 are both 0, we can simulate this. Here we have to set the value of input 1. Let input 1 is equal to 1 and all of the others are the 0, and at control 1 and control 2 also 0. Now we run this. It shows the output 1 because the input 1 is equal to 0. At control when the control 1 and control 2 are both are 0, then it shows the input 1 at the output. So input 1 is equal to 1, so show the 1 at the output. So we can see there output show 1 as similarly to the input 1. Now we run, we change the value. Here we do the input 2 is equal to 1 and we change the condition. Control 1 is equal to 0 and control 2 is equal to 1. Now we simulate this. Now it shows the input 2 at the output. Here it shows the output as shown here. When the control 2 is equal to control 1 is equal to 0 and control 2 is equal to 1 and input 2 is equal to 1, then the output is equal to input 2. Now we again we do this 1 and 0. It has 4 cases. Now this, and we do this 1 and this 0. Now we run this. At this situation it shows the input 3 at the output. At this situation we can see that when the control 1 is equal to 1 and control 2 is equal to 0 and input 3 is equal to 1, and then the output is similar to the input 3 here, because input 3 is equal to 1 and output is also a 1. Now our last case is we do the input for 1 and all the other are 3. Now control 1 and control 2 both are 0. Now it implements the input 4 on the output. Here we can see that when the input 4 is equal to 1 and both of the control switches are the 1 1, then the output is equal to input 4. So that's the first method of the 4x1 multiplexer in the implementation of the 4x1 multiplexer in the Verilog code. Now we discuss the second method here. Here is the second method, which is the logic statement implementation. In the logic state implementation, here is sign out. Discuss here the 4 cases. It is we can study it as when it shows the input 1, then the situation is not control 1 means the 0 at control 1, and not control 2 means 0 at control 2. The situation is 0 0, and when the input is equal to 2, it shows the not control 1 at control 1 is equal to 0 and control 2 is equal to 1. Similarly at input 3, control 1 has 1 value and control 2 is equal to not, it has 0. Similarly at input 4, both are the control 1 and control 2 have the 1 1. And similarly we test this into the quarter software. Simply we copy this and go to the quarter. Now let we select the Verilog HDL file and paste it here. Here we for the setting. Here we can explain the output here. When the situation is 0 0, then the input 1 is applied on the output, otherwise input 1 is equal to 0. When the situation is 0 1, and then the input 3 is applied and all the other 3 situations are 0. When the input is 1 1, then the input 4 is applied at the output and all the input 1 2 3 are the 0, because they are connected by the OR gate here. 0 plus 0 plus 0 plus 1 is equal to 1 and the output is equal to 1. Now we run the study. We have to change the name here. Here is the name M2. Now we run this again. We can see here the full compilation was successful, and we can see the RTL view by locating in RTL viewer. Here is the RTL view of this. Now here is the situation of the not, because both the inputs are 0 here, and not become converted into the 1 1. When 1 1 is multiplied, the output is equal to 1. So the output become input 1. Here is the situation of 0 1. Because 1 0 at 1, it directly pass through the NAND gate, and when here is a 0, and pass through the NAND gate, and it also converted into the 1 1. Here is the situation of 1 1. So we don't need to implement here the NOT gate. So here at input 3, here is the situation of 0 1. And not get converted, convert the situation into the 1 1. So, so it has 4 cases. Now we go to the university program EWF to see the waveform. Here we insert the node finder here and list it here, and okay. Here we can see that input these are the 2 control switches, and these are the 4 inputs. When the control 1 and control 2 are the 0, and we set it shows the output input 1 is at the output. So we edit the input 1 by 1, so and all the other outputs are the 0 0. Now we run this, and it shows the 1 at the output. Run the simulation. You can see here when both of the control switches are the 0 0, and then it shows the input 1 at the output. Input 1 is also 0 and output is also 0. Similarly, we perform the other cases when the input is equal to 0, control 2 is equal to 1, and control 1 is equal to 0. Then it shows the output 2. Now we run this study again. Here we can see that when the control 2 is equal to 1 and control 2 is equal to 0, and in this case control 1 pass through the control not control 1, and the situation become at input 2, and it shows the input 2 at the output. Similarly, now we go to the similarly the other operation are performed. We study the case 1 1 here, and input 4 is equal to 1 and input 2 is equal to 0. Now we run this. Now it shows the output at input 4 is shown at the output, because both the input control 1 and control 2 are the 1 1. Here is the we can see that when control 1 and control 2 both are the 1 1, it shows input 4 at the output. Now that's all for this case, and now we study the next method here. And third method is the case statement implementation. Here is the similarly module and declare the variables here and declare the input output. And the new thing is in this is this reg out and always at the rate of input output all the inputs. It is used to continuous updating the output according to the situation. In this we use the case statement as shown by the name. We do the case study. Here we use the case study of control 1 and control 2. Here the first case is when the control 1 and control 2 both are 0, the output is equal to input 1. Similarly, at the second case, when the output is equal to 0 1, it means at control 2 is equal to 0 and control 1 is equal to 0 and control 2 is equal to 1. The output is equal to input 2. And similarly, when is equal to 1 0, the output is equal to input 3. And when both of the controls are the 1 1, then the output is equal to 1 4. And we don't use the display in the other cases. We use the display default display. If all of the cases are not available, then it shows the please check control bits as we use in the C++ programming. For the implementation of test, we here we end case and end the module. For the test, we simply copy it and go to the Quarter software. Now here we select the Verilog HDL file and we paste it here. Here is the 4 cases, and now we run the study. Here we need to change the file name, which is equal to m3. Here is the case implementation. Method. The module is equal to m3. Declare the variables, declare the output input, registered out always at the rate it's used because it continuously update the output according to the cases. And use the default display. When all the situations are not implemented, then it shows the please check control bits, and here it ends the cases and end the module here. Now we run the study. We can see that the full compilation was successful. Now we can verify the RTL view here. Here it shows the 4x1 mux here. Here is the control 1 and control 2 two knobs, and the input 1, input 3, input 2 and 4 are the 4 inputs, and one output, so it is the 4x1 mux. Now we go to the university program VWF to create the waveform. Here we insert the node and node finder here, list it here, copy and OK. When the both are the 0, input 1 is implemented. output shows the 1 on the, because when the both cases are the input control 1 control 2 are the 0 0, then the input 1 is implemented on output. You can see here output is equal to input 1. Now when it is equal to 0 1 or 1 0, now it shows the input 3 on the now in this case we can see here it shows the input 3 on the output. When it is equal to 1 and 0, it shows the input 3 on the output. Now when the both are the cases are the 0, control 1 and control 2 are both 0, then it shows the input 4 on the screen. We do all the other are 0. Now we run the study again. We can see in the output the output is equal to input 4 when the both of the control 1 and control 2 are the 1 1. So all the three cases are the verified. All three cases are verified. And now the here next is the example of the mux. Here is the same 4x1 mux multiplier, and here he changed the name. Above is the name input 1 2 and 3 4. Here he changed the name D0 D1 D2 and D3, and output is equal to Q, and change the control 1 and control 2 into select 1 and select 0 select. Here it shows the example Verilog for code for the multiplexer implementation using sine model. Sine it is the example of the first one method. No, it is implementation of the 4x1 multiplier using a sine. It use a sine here. Output is equal to deselect. It means output is equal to input depends upon the what we select from here. At this situation, when the select is equal to 1 0, then it shows the output D1. Here is simply a module and a file name, and declare the input and output. Here it define the wire. We can define it or may not be, and here is sine output is equal to input, and here select is equal to control. It depends upon the what we select from here. If we select the 0 0, then output is equal to D1 D0. When we select the 0 1, the output is equal to D1. When we select 1 0, the output is equal to D2, and similarly we select the 1 1, the output is equal to D3. Here we have to simply select this example. And go to the Verilog HDL file here and paste it here. Here is the method 4 of the 4x1 multiplexer. Here is the assign is equal to main body of the code is this. Assign q is equal to output and d is equal to input. Assign output is equal to d depends upon what is selected. Now we run this study. We need to change the name of file, which is equal to e1. Now we run this study again. Here we can see that the full compilation was successful. Here we can verify the RTL view by locating in RTL viewer. Here is the RTL view of mux. Here is a d is equal to 4 bit mux and select is equal to 2 bit, which is equal to 1 0, and so output is equal to 1 bit. Also there is a 4x1 mux. Now we go to the university program VWF to locate the waveform. Here we insert the node and a node finder, list it here, copy this and okay. Here is a D input, which is the 4-bit input, and Q is equal to output and select is equal to control switches. If the select are the 0 0, and then the input D0 is equal to shown on display on output. We select the when we do the select both 0 0 and here D0 is equal to 1. We can see there after the simulation the output is equal to D0, which is equal to 1. We run the simulation here. Here we can see that there is output. At output it shows the 1. This is the output line, which is equal to 1. Only the D0 is equal to 1 in all these stages, so it show output is equal to D0. In the second case, we do it is 0 and D2 is equal to 1 and select 1 and 2, select 1 is equal to 1. When the select is equal to 1 0, it then the D2 is displayed on the output. Now we'll run this study again. Here it shows the output screen. We can see here when the select is equal to 1 0, and it shows the D2 on the output screen. Q is equal to output and D2 is equal to 1 and D2 Q is equal to also 1. So now we study the last case here when the D3 is equal to 1 and all are 0, other are 0, and we select 1 1 here. Now we simulate this again. When the both controls are the select are the 1 1, and then it shows the 1 D3 on the output. D3 is equal to 1, and so it shows the 1 on the output screen. We can see here the simulation is running. Here we can see that when the both are selected as 1 1, it shows the D3 on the output. So this case is also verified. Now we go to the next case, which is the using the always block. We use the always block. Similarly, as the previous, we declare the input, output, and register output. We use the wire select and wire D, which is the output, a 4-bit in output, and always D. We use the always D output or select. It always it is used to continues updating or refreshing the selected one output and select controls, and here the output is equal to similar above as above. Output is equal to input and depend upon the select what is selected on the this. Now we also copy this and run the study simulation on the Cortex to test this. Here we go to the Verilog HDL file and paste it here. Four cross one mux using always is used for the continuously updating. Now we run the study. Here we have to change the name of the file. E2. Now we run the study again. We can see here the full compilation was successful. Now we verified the RTL viewer. Here we can see that inputs are the 4-bit input and output is equal to 1 bit, and selected control are the 2 bits. So here is the 4+1 mux. Now we go to the University program VWF. Here we insert the node finder here, list, and copy this. Okay. Here D is a 4-bit input and select is a 2-bit. When we select the 0 0, it shows the D1 D0 on the output. When we select the D0 is equal to 1. Now we run the study. It shows the D1 on the output. Here it shows the output screen. Here it shows the D0 on the output. D0 is equal to 1 and Q is also 1. Now we study the second case. Here we select D0 is equal to 1, and when it is equal to D2 is equal to 1, and here we select D1 is equal to 1. Now we run the study again. It shows the T1 on the output. Here we can see that when the select condition is equal to 0 1, and it shows the D1 on the output screen. The output D1 is equal to 1 and Q is equal to also 1. Now we study here the last case. When both are these 1 1, then it shows the D3 on the output. Now we run the study again. And show here the output. When the both cases are 0 0, it shows the D3 on the output screen. It is explained on the from the circuit which is present on the top of this. Here control 1 and control 2 are the select here, and input 1 is equal to D0, input 2 is equal to D1, it is equal to D2, and input 4 is equal to D3, and output is equal to Q. Here we study this case in all these situations. Now we study the next case here. The next case is equal to if statement, using if statement. In if statement we use as regular we declare the input output. Here we register Q and wires. We use the always statement to continue refreshing the select or D, and here we begin the if statement. In if statement it has the if conditions. If select is equal to 0, it means if there's both selected are the 0 0. If we select the 0, then Q is equal to D0. Q is equal to D0. Then if we select the second case is if we select the 1, then the Q is equal to D1, and the third case is if we select 2, Q is equal to D3. Continuously if we select the D select is equal to 3, then it shows the Q is equal to D3 as shown here. Here is and the if conditions, and here and the module. We simply copy this and go to the quarters. Now we select the Verilog HDL file here and paste it here. We have to delete this log. Here is a model, and here we added the file name which is equal to E3, and select Q, select and Q are the inputs and Q is the output. Here declare it, and here register Q, which always at the rate it continuously update the select and the output according to the given situation. Here the code begins if statements. If we select 0, then then output is equal to this. If we select 1, then the output is equal to D1. If we select 2, then the output is equal to D2, and if we select 3, then the output is equal to D3. Now we run the simulation. Here we write if statement implementation. Now we run the study. here compiled successfully, compilation was successful. Now we go to the RTL view. Here we locate the in RTL view 4x1 mux. Here it shows the select one, and here is a input 4-bit input, and here is a 1-bit output, and here is select one selecting condition. Here is a 4 cases which is defined in the program coding, which are this is logical equality. You use the logical equality or symbol. She show here the logical equality symbols, and here is the circuit of the 4x1 mux. Now we go to the university program VWF by selecting this. Here we insert the node here and find list it, copy this, and okay. Here is a D input which is 4-bit, and select this. If we convert it into unsigned decimal, now when it is equal to 1, what will it show? At we select the 0 0. Now we go to this. Here is when if we select is equal to 0, then Q is equal to D0. Now we go to the here, we convert back it into the binary, and when the select is equal to 1, we convert into unsigned decimal, and set is equal to, when it is equal to 0, we study the case first. If select is equal to 0, then it shows the D0. Select is equal to 0, it shows the D0 which is equal to 1. Output is equal to 1. Here we can see it shows this when the select is equal to 0, it display D0, Q is equal to D0, as in the program code. When select is equal to 0, Q is equal to D0, and when select is equal to 1, Q is equal to D1. Now we go to this. When select is equal to 1, we selected the 1, and the output is equal to D1. We set the D1 is equal to 1, and all the others is 0. Here we can see that Q is equal to D2 here. When select is equal to 1, Q is equal to D2. When select is equal to 1, Q is equal to D1. We again see this. When select is equal to 1, D1 is equal to Q. Similarly, when the select is equal to 2, it shows Q is equal to D2. Now we study the last case. If select is equal to 3, here Q is equal to D3. Now we select the is equal to 3 here. It shows the D3 on the output. D3 is equal to Q. Now we run the simulation. Here it shows the output screen. You can see that when select is equal to 3, then Q is equal to T3. This case is also verified. This method is also verified. Now we go to the next method, which is the using the conditional statement. As the previous, it declares the input output here, and whilst it assigned the conditions here. In this condition, we can define is when select is equal to logical equality is equal to 0, then what question mark shows, and then it is equal to D0, then the output is equal to D0. When the select is equal to 1, then out Q is equal to D1. Similarly, when the select is equal to 2, then the Q is equal to D2, and else it is equal to D3. It use the if and else statement here, as shown above. If select is equal to 0, Q is equal to D0, else if select is equal to 1, then Q is equal to D1, else if select it use the else if statement, and at this it use the else only. And here we end the module. We copy this simply and run the simulation on Cortex. And now we go to the Verilog. Here we select the Verilog HDL file and paste it here. And here we write the conditional study using conditional statement. Using conditional statement. It is the last method to implement this. Here we have to change the name of the file, which is equal to E4, and select and DR the inputs, and Q is equal to output, and declare the wires and assign the main body of this. If Q is equal to if select is equal to 0, then Q is equal to D0. If select is equal to 1, then Q is equal to D1. If select else if is select is equal to 0, then Q is equal to D2, else D is equal to 3. We run the study here. Next to save. Here we can see that the full compilation was successful, and we verify this by locating the RTL view. Here it used the logical equality, and these are the 3 logical equality symbols, and here is the input, 4-bit input, and 4-bit, and here is a 1-bit output, a 4x1 circuit, mux circuit, and here is used the if else statement. Now we go to the university program VWF. We go to the university program VWF. Okay, here we insert the node finder here, list it, and copy this this side and OK. Here D is equal to this, and in the program he shows when the select is equal to 0, it shows the D0. Now we go to this, we convert it to unsigned decimal and change this into when it is 0, it shows the D0 is equal to Q. We run the simulation. OK. And simulate this. Here in output screen we can see that when the select is equal to 0, then it shows Q is equal to D0. In the second case, when D2 is equal to 1, and it shows the D2 here, 2 here. When it is equal to 2, 1, 0, it shows the D2 is equal to Q. We run the simulation here. Here in the output screen, it shows when select is equal to 2, then it shows D2 is equal to Q. Q is equal to D2. Now we study the last case here. When the select is equal to 1 and select is equal to 2, it shows the D2. Else in all other condition it shows the D3. If we select 3, it shows D3. If we select 4 and any else number without 0, 1, 2, it shows the D3 here. Now we test this. Here is the D3. We select this 1 and 0 here, and we select this and select here. Let's suppose we select this 5 here. It's use the else statement here. Using else statement, it shows here D3 on the output. Here in output, it is 1. Here it is 0, it is 2 and 1. Here we have selected 1, then it shows the D0 on the output, D1 on the output. D1 is equal to 0 and Q is equal to 0. We have to select the here again 3 here, and then we run the simulation again. Here is the simulation. When we select the 3 here, we can see that Q is equal to D3. Use the else statement as shown here in this. else d is equal to 3. When we select 0, any number without 0, 1 and 2, it shows the T3 on the output. So all the methods ends here. That's all methods to implement the one circuit by the different ways. We define the implementation of the multiplexer using different ways. So that's all for